be talking just quickly a little bit about some of the recent news and outcomes, as you mentioned with the telescope, but also a number of really great successes this year in civilian space travel. I currently work after RSI. I continued my research in aerospace engineering. My focus has been on combustion and propulsion technologies. Currently work down here at DevCom Army Research Lab, helping to lead a program looking at what do we do in the future for power and energy, particularly for robots and ground systems, flying systems. How do those team and pair? Everything from biofuels, what is the right amount of hybrid electric for which kind of robot, how big it is, what is it going to be doing its tasks. Teams of robots, right? If you need something accomplished, how do they work together as a team and share energy amongst themselves and make autonomous decisions about which robot should do which task. So those are kind of the research areas we're leading. Today I was going to just say a few words on kind of space travel specifically. So if you've been watching the news, you probably caught at least a couple of these things, but there's been a lot going on, right? We've had multiple companies been able to successfully launch reusable rockets, taking people up into space. A flurry of those across the late summer into the early fall. We've had the first all-civilian spaceflight, right? Actually orbiting, not just launching up to the edge of space and coming back down, but orbiting was in September. A couple other milestones, right? This was a recent launch where they've used the same rocket stage, what they say, 5 or 9 times or something. So reusableness, this idea of being able to really start cutting down costs and make this more accessible to science, to technology, to development. So in some ways, we've solved the hard part, but it's also more the easy part. And what do I mean by that, right? The difficulty of getting to space is really how fast you have to go to stay in orbit. And so much of this is just accelerating your spacecraft up to that velocity. So some different numbers, right? Getting off the surface of the Earth, you're looking about 8 kilometers a second. And fortunately, once you're up there, it's easier to go other places, right? So getting over to the moon, 4 to 6. Getting over to some of these asteroids that we're interested in, maybe about 4. So the hard part was getting up there in the first place. But at the same time, I call that the easy part because what we're doing on a lot of these rockets is kind of just updating and modernizing the designs and technologies that we had in the Apollo space program and working on making that a reusable platform. So there are a lot of very interesting engineering technology challenges for that. But at a certain level, we're kind of stuck in this tyranny of the rocket equation problem, right? So if I want to send a pound of mass to space, I'm generally going to need just a bit under a pound of fuel. And then that pound of fuel needs just a little, or just under a pound of fuel needs just under a pound of more fuel to get it going. So you end up with these structures where, you're 85% fuel mass and another 10 to 12% structure to hold that fuel. And you're only putting 1 to 3% of your vehicle is actually what you wanted to take to space in the first place. So these are all kind of the challenges of how we do space travel. And like I said, we've solved one of the hardest parts, which was escaping Earth's gravity well. But there's a lot of other challenges now that you solved one problem, you're rewarded with 2 new ones. And so kind of looking out at what some of those things are, this is a chart that NASA put out recently to kind of help researchers and civilian and everyone make estimates about, how do we keep people alive on these missions? So everything from the air, how they'll live, how they'll eat, how they'll get water, how we keep them conditioned to be the right temperature, right? The parts of space where it's very hot and the parts of space where it's very cold. And right now, basically all these missions that we've been doing and all these recent successes we had this year and in the last 5 years are these what we're calling very short missions. And when you think about that, because you're just going up and back and you're not up there for more than maybe a day, you don't have to have a lot of these concerns. You can just bring all your trash home. You can use a lot of disposable things. But when we start branching out to where we want to go in civilian space travel, we're talking about things like, let's go up to the moon. Even if that's tourism or if that's long-term to deploy into a habitat, that's basically an 8-day, a 7-day trip there and back, about a day on the moon. So you're in this kind of second bar. Or if we're up there currently on the ISS, right, you tend to be on the order of this pink blocks here. We start talking about things like going out to Mars or out to somewhere where you're trying to mine a specific surface or some of the other applications. We're into this long term. We're into things that are very reusable. growing food, not just bringing it with you? How do we make sure that we try and recover every ounce of water possible? Don't waste anything. And so kind of depending on, we were able to focus a lot in the civilian space here in these missions because you didn't have a lot of those concerns. And so we solved that, and now we get to come on to the fun problems, right? On how do we do power and energy? How do we do water? How do we do waste? And so some of those ongoing challenges, right, that are always going to be there in space. It's the ultimate austere or extreme habitat, right? When we design things in the civilian space here on Earth, most of your electronics, you get to go home and you get to plug them into an outlet. There are no outlets up there, right? If I dropped my kids off at school today and they forgot their coats, well, we just ran home, turn the car around, go get your coat, put it back with them. But if you forget your coat on the spacecraft, that's it. You're up there. You're not coming back, right? So there's also there's not a gas station, right? We've talked about there's concepts for how do we build a gas station up on the moon or something along the way to make this easier. How do we when we built the ISS, right? They sent up multiple launches with multiple components that all got assembled up there. We didn't launch it all at the same time, which leads to kind of one of the other greater challenges of space is how do you do manufacturing? How do we build things? How do we build not just spare parts, but fuel, food, other things? A lot of our industrial processes, when you think about it, rely on gravity. When you go to weld one of these fuel tanks together, right, getting that weld to go to the place you intend and to stick there while it solidifies is reliant on a gravity. So how do we have to redesign our manufacturing process to go up into outer space? How do we do, actually fully self-enclosed self-sufficiency? And I think one of our speakers today will be talking about that. But I remember as a child hearing about Biosphere 2, right? The great experiment that they were going to lock themselves in this environment and be fully self-sufficient, and all the challenges they had and weren't able to realize at that time in the early 90s, and where we've come since then. Also, a couple pitches here. So we talked about, right, this asteroid that just came. This was on Saturday, right? The asteroid came into its nearest orbit to Earth. And so it didn't hit us, but like they're talking about, that was some significant amounts of cobalt, of nickel, some of these precious metals that are very rare on Earth that we could go up there and possibly get, right? Cobalt is in significant demand for all of the electric vehicle batteries that we want to, if we want to transition to an electric vehicle fleet, we're going to need a lot more cobalt. Also, DARPA, right? They just announced right before Thanksgiving, so it probably got lost in a lot of the announcements, but biomanufacturing for space, right? Can we send a pod up somewhere that has bacteria that are designed to grow different things, not just food sources or biofuels the way we think of, but can they start growing where their waste product is building blocks for structures? And also, I'll put a little pitch in there, right, with some of our area. Where does autonomy play in this, right? We send rovers up right now to Mars, and they do limited scientific tasks. And part of that is a communications problem, right? I don't have an astronaut next to them that can help fix things or retask them. But part of it's also a limitation in the ability of autonomy right now. So if we envision this future, likely these astronauts will have some robotic partner. So how do we do human agent teaming and those kind of functions in space?